Okay, let's pick up where we left in the last class. If you recall, we've started working more and more on designing state feedback control, which is also known as pole placement. So if a system is controllable, that means we can place its open loop or relocate its open loop eigenvalues or poles anywhere on the complex plane we want. And we've been working on methodologies in solving the problems with hand, as well as using MATLAB to find the proper control gains to place the eigenvalues where we want them to be. And of course, we choose the eigenvalues to create a certain behavior in the system. Furthermore, we talked about the next component in a state feedback controller, which we call pre-filter, another gain that guarantees that the steady state error goes to zero. So Y matches R in steady state. So this was the problem that we started working on. A mass attached to a damper and a spring, and it's under effect of an external force, horizontal force. There is no friction between mass, so the movement of mass is not affected by friction. So we came up with the differential equation. We identified the state vectors, we identified the input, and we decided that we wanted to look at two different cases. Once the output was displacement, the other case output was velocity. We wanted to know if which one of these two cases created a controllable system. And so we created matrices A and B and C. There are two C matrices, one for when we go with the first choice when the output is displacement, and the second C is for when the output is velocity. Immediately, it should be clear that the choice of matrix C has no bearing on controllability of the system, because controllability is determined with the WR matrix, and there is no C involvement in there. It's only B and A. So this was a second order system. So that meant in the controllability matrix, the highest power of A was going to be 1. So the matrix therefore is made of B as the first column, AB as the second column. So it's going to be a 2 by 2 matrix because the order of the system is 2. So as long as WR is non-zero, or the determinant of WR is non-zero, we have a controllable system. So we found what A times B was, and we already knew what B was. So we formed the reachability matrix. This is B, and this is A times B as we calculated here. Then we looked at the determinant, and it is clear as long as M is not very large, as long as M is not approaching infinity for this system, the system would remain controllable. So we went one step further and said, with the full state feedback control, with the method of pole placement, we want to achieve a natural frequency of 1 radians per second and have a critically damped system. That meant that the two eigenvalues of the closed loop system had to be located at -1 and -1. And we also assumed some numerical values for M, K, and B, which means for open loop, so before any control, for open loop, when M is 1, K is 1, and B is 1, so for open loop, so these are desired values for closed loop. For open loop, we have a natural frequency of 1. So natural frequency of open loop is 1 radians per second. And what is the damping ratio of open loop? Can you calculate the damping ratio of the open loop with M of 1, K of 1, and B of 1.4? What is the damping ratio of open loop? Or how would you calculate it if you have M, B, and K? The approach to calculate it is by realizing that the base differential equation is this: m x double dot plus bx dot plus kx equals force. This is the base differential equation that we got. And in order to arrive at this standard form, we divide by m. So this becomes x double dot plus b over m x dot plus k over m x is equal to f divided by m, which is also can be written as x double dot plus 2 zeta omega n x dot plus omega n squared x is still equal to f over m. So by comparison, it should be easy to calculate natural frequency and damping ratio if you have b, m, and k. So if you have k and m of 1 and 1, it's easy to see that k over m is 1, which is equal to natural frequency squared, so natural frequency is 1. Now, if natural frequency is 1, 2 times zeta times natural frequency is equal to b over m. In this case, b over m is what? So b over m, which is 1.4, is equal to 2 times zeta times omega n, and omega n is 1, so from here you can calculate zeta as 0.7. So what are we trying to achieve? We are trying to maintain the same natural frequency. Maintaining same natural frequency means we are not trying to change the distance of the eigenvalues. We are rather trying to displacement such that the damping ratio goes from 0.7 to 1. So the damping ratio goes from 0.7 to 1. And what is the next step? Now that we know where we want the eigenvalues to be located, we need to design the controller to place the poles where we want the two poles to be. Now, if you look at the complex plane, for open loop, you have omega n of 1, zeta of 0.7, so you have this. So you have a pair of poles that are located here and here. And what you're trying to do is to maintain the distance, but bring them both on the real axis. So you're trying to bring them as if they're moving on a circle and bring them exactly on the real axis where the damping ratio is exactly equal to 1. So you want to bring them both here. So the distance is the same. So if this is omega n, the distance, this distance remains the same. It's just the angle that the two eigenvalues make with the real axis. That's 0.7 is sine of 45 degrees. So it's initially at 45 degrees to the imaginary axis. You're trying to make that angle equal to 90 degrees. So you have a critically damped system. Okay, so what's the next step? How can we design this controller to put the eigenvalues where we want them to be? What is the next step? So I'm going to wait for you to suggest something, and I will take that suggestion. What we have so far is A, B, and C of the open loop, and we also know where we want the eigenvalues to be located for closed loop. And we also determined that this system is controllable. So it's possible to relocate the open loop eigenvalues to anywhere else on the complex plane. Still waiting for you? So the question is, what is the next step in designing the controller? And the controller looks like this. So we have the system, what we call the process, and we are in the pole placement process. In the state feedback process, we feedback x as a vector multiplied by k as another vector with a negative sign, and from here we bring r with the pre-filter, and that's how we create the input to the open loop, and that's the process of placing the eigenvalues where we want to be. So the design means finding values of k to create vector of k, and also finding this scalar pre-filter. So my question to you still stands. The question I have for you is, how do we find k and kr? What is the next step in design? Yes.
So you said we want to find K and KR next, correct?
Correct. How do we go about it?
So for KR, we have the formula -1 over C times A minus BK inverse times B.
So you're saying for kr we have a formula.
Yes.
And that requires A. So that's the formula that you're talking about. I brought it on this slide. You're saying,
Yep.
I need C, I need A, I need B, and I need K in order to calculate it. Great.
Yeah.
So that's that step. But don't we need K to calculate KR? So how do I find K then? So we solved part of the problem. We figured part of the puzzle. But how do we find K? We need K in order to calculate the pre-filter. Yes.
Would it be finding the closed loop and then looking at those eigenvalues?
Yeah, absolutely. So the methodology, if you're doing it through an analytical solution, is to form the A matrix of the closed loop, find those eigenvalues, and set those eigenvalues where you want them to be. So that's this. Please remember that. So, and what is the A matrix of the closed loop? I have it on this slide. It's A matrix of the open loop minus B, which is B matrix of the open loop, times K, which is the vector that we are trying to find. It's unknown at this time. So in this formula, this is known, but this is unknown. The other thing that we know is we want to place the eigenvalues of the closed loop here. So we have three pieces of information. So we know A, we know B, we know where we want the eigenvalues to be located, but we don't know K, and we are going to find K through that process. So let's go ahead, or should I give you some time? Let me give you some time to form A minus BK, form a closed loop, and find K so the eigenvalues are both located at -1, -1. So I'll give you a minute to set it up. So we know the parameters of the system. So we found A matrix to be 0, 1 minus K over M minus B over M. So if you put the numbers down for them, A becomes 0, 1 minus 1 minus 1.4. And B is 0, 1 over M. So you substitute for M, it becomes 0 and 1. So the next step is to form a closed loop, which is A minus BK. So let's find BK first. B is 0, 1. K is a row matrix, a row vector rather. K1 and K2. How do we know there are two Ks? It's a second order system. Number of Ks are equal to number of state variables. So there are two of them. If you multiply B by K, you get this 2 by 2 matrix which has 0, 0 on the first row, K1, K2 on the second row. Now if you subtract BK from A, which we have up here, you get 0, 1, minus 1 minus K1 minus 1.5 minus K2. So that's our A minus BK, which is A of closed loop. We know where we want the eigenvalues of this matrix to be located. That's given to us as part of the specifications for the problem. So the next step is to find the eigenvalues of a closed loop and set them equal to the eigenvalues that we want the matrix to have. So how do we find eigenvalues of a matrix? You said what determinant? The determinant is determinant of lambda I minus a closed loop. Very good. So lambda I, a closed loop. You create the determinant and set it equal to 0. That's how you find the eigenvalues. So let's go and create this determinant. I'm going to do it in one shot. So lambda I minus a would be lambda here minus 1 here, because a is being subtracted, so all elements get it automatically a negative sign. So this becomes 1 plus k1 because of the negative sign, and this becomes lambda plus 1.4 plus k2. This is determinant of lambda I minus a, and that is should be equal to 0 in order for us to find the eigenvalues. Do you agree? Let me know if you don't agree or a step needs further explanation. So if you find the determinant, it becomes lambda squared plus 1.4 plus k2 times lambda plus 1.4 plus, no, you don't have that. Okay, I apologize. So multiplying lambda by this, you get these two terms, and then it's multiplying these two off diagonal terms and subtracting them, which will give you a plus sign. So plus 1 plus k1 equals 0. That is the characteristic equation. Okay? Any questions so far? This characteristic equation with proper values for k1 and k2 should give you another characteristic equation that will give you two roots, both located at -1, which means the characteristic equation that we want is like that. So what we want to have is this. We want to have lambda plus 1 times lambda plus 1. Because if you set this equal to 0, there are two roots, and both roots are located at -1. That's what we want. So let's find this polynomial. So if you multiply this, you get lambda squared plus 2 lambda plus 1 equals 0. That is the characteristic equation that has two roots, both located at -1. And in order for us to put the eigenvalues of the closed loop at -1, -1, essentially this should be identical to this. That's the only way. That characteristic equation that we got for our closed loop system should match the characteristic equation that produces two eigenvalues at -1. That's how it works. So based on that, can you go ahead and find k1 and k2? So k1 is? K1 is 0. K1 is 0. And K2 is? Did someone say 0.6? K2 is 0.6. So what does it mean K1 be equal to 0? K1 being equal to 0 means what? Means the gain that you multiply by which one of the two state variables is equal to 0? By the first member, by the first state variable is 0. So when you feed back displacement, you multiply it by a gain of 0, which means essentially you're not feeding back displacement. You're just simply feeding back velocity in this special case. Now, why did this happen? Why do we have a K1 equals 0? The reason is we are not trying to increase omega n. So we are happy with omega n we have. The only effect we are trying to make is just on the damping. So we are not using full possibilities or full potential of pole placement. That's why in this specific case, K1 turns out to be 0. And it should be easy to see that if you, for example, say, now my desire is something else. Let's solve another problem. You can say, I want for closed loop. So I want for closed loop to have an omega n of 5 radians per second and zeta of 1, you should find another set of control again. So please go ahead and find those. So with these two values of omega n and zeta, you have this characteristic equation. So for a standard second order system, you have lambda squared plus 2 zeta omega n lambda plus omega n squared. That's the standard characteristic equation for a second order system with lambda and omega n. So if you substitute for lambda and omega n in this equation, zeta is 1, I'm sorry, if you substitute for omega n and zeta rather, so lambda is unknown. So if you substitute, you get to this characteristic equation, lambda squared plus 2 lambda plus 25. And how do you find K1 and K2? Simply by comparing this equation to the equation that we have up here in yellow. So what you know is 1 plus 4 times plus K2 has to be equal to 2. and 1 plus k1 has to be equal to 25. Yes, mistake? So it should be 10 lambda. Yes, here? Yeah, I forgot to multiply it by 5. So this should be 10. Yeah, thank you. Let me make that correction. Here, right? Okay, thank you. So this has to be 10 lambda. Everything else is okay? Okay, so the two equations we have is, so 1.4 plus k1 has to be equal to 10. And the next equation is 1, this is plus k2 rather. Plus k2 is 10. And then the next equation is 1 plus k1 is 25. So you find k2 to be 8.6, and you find k1 to be 24. So if you have MATLAB open, please create a state space model with A, B, C, and D matrices that we found for the open loop. And then first simulate the open loop. So give it a step input. Because the open loop is underdamped, it should show oscillation. So what we want to show is by proper control, you can actually stop that oscillation. So now the closed loop system rather will no longer oscillate. So I'm going to follow along in the online version, but please you use the Simulink so you get more practice with Simulink. I'm using MATLAB, so I'm creating the A matrix, the B matrix, the C matrix, so the displacement is the output. So system created as a state space with A, B, C, and D matrices. The first step for me is to make sure I have the proper eigenvalues of A are located at -7 plus minus 0.714. So if you look at PZ map the system, you have two eigenvalues for the open loop, a pair of complex conjugate, which is associated with natural frequency of 1 and damping ratio of 0.7. Let me know as you work with Simulink. If you have any questions, raise your hand. I'll come to you and I'll show you how to do it.
Did anyone get their MATLAB to open?
Oh, there's an issue with MATLAB?
Yeah, it's not pulling up.
Is there a second version of MATLAB? Sometimes they have another copy of MATLAB. Maybe we have the same issue here.
I think they only have 2015.
Oh, and it doesn't open up? Okay, I'm sorry for that. So why don't we do it together on the online version then? That's okay. So we have, I gave A, B, C, and D, the four matrices, and created a state space model. So I already created the state space model. by defining A, B, C, D, the four matrices. So let me bring them up one more time. So A, B, C, and D. And if you look at, so you define A, B, and C, and A, B, C, and D, and then you create a system with state space command, state space A, B, C, and D. That basically says, okay, I have a model made of these four matrices. And then once you have it, you can, excuse me, you can look at pole zero map with the command pzmap, and that creates this image that I have now on the board. So it gives you the fact that this system has two eigenvalues located at, you can also find the numerical value for the eigenvalues by the command eig. So eigenvalues of matrix A are located at -7 plus minus 0.7 times j. So a pair of complex conjugate. MATLAB, by the way, opens. If you click on that folder a few times, it does open if you are still interested in looking at the. Okay, so this is the open loop behavior. And if you create a step response, so if you type step for and system, you can see our expectation is that you'll get an oscillatory system. So you can see there is an overshoot, and if the simulation time was longer, you could see that it actually goes up and down a few times before it settles. Remember, 0.7 is still not a low level of damping. It's a high damping, so that's why the overshoot is not as high. Then in MATLAB, so we said we want the closed loop eigenvalues to be located at -1, -1. So I'm going to create a vector closed loop eig equals -1 semicolon -1. So I created a column for the two eigenvalues. And then I'm going to use the place command. So k, the control again vector, is equal to place of, I'll give it a and b of open loop, and I'll give it the vector in which I have stored the desired location of the closed loop eigenvalue. So closed loop eigenvalue. So I'll give it the A matrix, B matrix, both come from the open loop. And then I'll give it the desired value of eigenvalues, and this command should help me in finding k. Do you remember when we solved this problem with hand what the values were? The values were 0 and 0.6. So what MATLAB gives you is not exactly 0, but practically 0. So it says K1 has to be 4 times e to power -16, which is effectively 0. And K2 is 0.6. So it's giving you those two. Okay. Yes.
If we're doing MATLAB, is this where we have to use the author function?
It's because it's repeated. Yeah, acre. It's ACKER for Ackermann, I think, formula. Okay. Now, how can I simulate now the closed loop system? The way is to recognize that A of closed loop is equal to what? A of closed loop is A minus B times K. Isn't it? A closed loop is A minus B times K. That's how we design our closed loop system. So that gives us a new A. So we are now going to create a closed loop system, which is state space model of A of closed loop. So we are no longer going to use A of open loop, A of closed loop, but B, C, and D remain the same. So the only thing that changes between open loop and closed loop is the A matrix, effectively A matrix. So that gives you a new system. And to make sure we have achieved what we wanted to achieve, we can look at the eigenvalues of A closed loop. Where should they be if we have calculated K values correctly? They should be located at? Where did we want them to be? At? We said we want the closed loop eigenvalues to be located at? -1, -1. So I'm checking to see with these controller gains that MATLAB has calculated for me if A closed loop has these eigenvalues. So how did I do it? I used the place command to calculate the controller gain, and then I created my A closed loop, which is A minus B times K. So once I previously had A and B, and now I have K by the place command. So I'm going to look at eigenvalues of A closed loop. And where are the two eigenvalues located? At -1, -1. Okay, so we have created the eigenvalues. With this pole placement, we have the eigenvalues. So let's go ahead and find the response of this system to a unit step. So what are we going to do? We are going to type step of which system? System closed loop. System closed loop. So if you hit enter, it generates the step response. Is there any oscillation in this response? No oscillation whatsoever. And it's even cooler if you look at step response of system next to system closed loop. I don't know if this allows me to do it. So to look at both step responses next to each other, open loop and closed loop. Yes, it does. So which one is open loop? Blue or green? Blue is open loop. It had zeta of 0.7, so we had a bit of oscillation. But for a closed loop, no oscillation anymore. So why don't you play with this a little bit more? So we designed another controller to place the eigenvalues so that we have natural frequency of 5. So go ahead and implement that and look at the step response next to these. So I'll give you a few minutes to work on this and create another simulation result with the K values that would place the eigenvalues such that omega n is 5 and zeta is 1. So, and if you have any questions, if you are not sure of any steps, raise your hand. I'll come to your station and I'll work with you. Yes.
How did you define the closed system?
We defined the closed loop system by its A matrix. So we said A of closed loop is A minus B times K. A was previously known. K we found by place command, right? And B was also known. So we created a new A matrix, and with that new A matrix, I recreated my state space system. So I gave it a new name. Let me bring the commands for you. So watch here at the bottom, you will see the commands that I've used. So here, this was the K command. So before that even, we defined where the eigenvalues were supposed to be, -1, -1. And I intentionally create a column vector. I create a column vector. It has to be in column vector, otherwise you get an error. So then I use the place command to find the controller gains that would put the eigenvalues at -1, -1. And then afterwards, I created A of closed loop. Do you see that? So I said A of closed loop, I know is A minus B times K for this type of control. And with that A closed loop, I recreated another system. I gave it a new name. I called it system closed loop, SS of A closed loop, B, C, and D. B, C, and D remain the same as open loop. And then I found the eigenvalues to make sure the eigenvalues are located where I want them to be. And then I looked at the step response. The other thing we can do is you can look at pole zero map of system closed loop to see where the two eigenvalues are located. And they're located at? It appears from the figure that they're located at two different places. But if you read the horizontal axis, you see that they're both located at -1. It's just a funny way of display that they're two, but they're identical at -1. Anybody else facing any difficulties in coding, or let me know if you need help. I will come to you. So as I've shown you before, you can create eigenvalues by values of omega and zeta by realizing that for a second order system, the two eigenvalues are located at minus zeta omega n plus minus j times omega n times square root of 1 minus zeta squared. So because I don't know the exact value of the eigenvalues, I only know for the second case that I want to create an omega n of 5 and zeta of 1. I type omega n is 5, zeta is 1, and then I type this command that closed loop eigenvalues are minus omega n times zeta plus j times omega n times sqrt of 1 minus zeta squared. And the next one is minus n zeta minus j times omega n sqrt of 1 minus zeta squared. So that should give us a pair of eigenvalues as we expect located at -5, -5. Because the distance is 5 and zeta is exactly 1. So we know by now, we have repeated this a few times, that whenever you want zeta exactly equal to 1, the eigenvalues, the pair, are repeated. They're real and repeated at -5. So now that we have this, we can repeat the place command. So we can go here and say, I want a pair of controller gains that will give me this new location for closed loop poles. So here it is. It says K1 has to be 24 and K2 is 8.6. Is that what we found also? Yeah, 8.6 and 24. So that's what we previously found. So with this K, we can then go ahead and calculate our A closed loop, which is A minus B times K. That is the next step. And with this A closed loop, the next step is to create the system of closed loop. So system closed loop is going to be a state space made of this A matrix, the new A matrix, B and C and D. So that's the next step. And the last step is to look at the response. Or maybe look at the pole zero map to see that they're exactly located at -5, -5. So it basically delivers what we want. And then we can look at the step response. We're going to look at the step response of the open loop next to the closed loop. So you can see closed loop is the green. So steady state's value of response is significantly smaller than 1, but there is no oscillation and the system is quite fast. So what we have lost a little bit is this in the steady state gain, which we can compensate by calculating Kr. So why don't you please go ahead and calculate Kr for this case. So Kr had an equation up here. So find that equation and I'll try to bring it up as well. So this is the equation for Kr. So use MATLAB, please, to calculate Kr. So it's -1 divided by C times A minus BK of open loop. A is open loop. So A minus BK is A of closed loop, essentially. So A minus BK is A of closed loop times B. So please calculate Kr. By looking at this plot, can you approximately tell me what Kr is supposed to be? This is, remember, this is the closed loop response. In step response, we want this to be exactly equal to 1, and roughly is less than 0.01. So Kr is at least 10. So we have to scale this up by 10. So let's calculate Kr. So Kr is -1 divided by C times inverse of, so I'm going to write it A minus B times K. This is inverse of this matrix times B. Let me double check the formula. So it's -1 over C times A minus BK inverse times B. So this means inverse of matrix A minus BK. So C times inverse of A times A minus B times K times B. Oh, what did I do? Oh, C is capital, so I typed the lowercase c. So Kr is 25. So this is actually 0.04. That's why we need to multiply it by 25 to get to where we want it to be. So this is the pre-filter that we calculated. So with this pre-filter, then we can get to the steady state response that we want. Any questions? Okay, I thought it might be a good idea to spend some time on the last quiz that I gave. So let's bring that up. So the first question of the quiz says a system has two poles at -1 and +1. Find the transfer function and state space model for this system. So there is no controller. We're just trying to find the transfer function and state space. So for transfer function g of s, it has two poles, so it can be seen as this, s plus 1 times s minus 1. So a transfer function like that has two poles. S plus 1 gives you a pole at -1, s minus 1 gives you a pole at +1. So this is the ratio of output over input. Now this system definitely is a second order system, isn't it? The highest power of S is 2, which means we have two state variables. So if you look at the block diagram, what happens is you bring U in to your first portion of the dynamics. Let's say this is S plus 1. And out comes one variable, which then goes to the second portion of the dynamics. And out comes Y. So U goes in and call this x1, your first state variable, and call this x2, your second state variable. The order could be switched, so you can call the line in between x2 and the next one x1. It doesn't really matter, as long as you realize that there are two state variables, and each is created this way with one dynamic. So we can basically write another set of transfer functions to say what we just did. So it's x1 over u is 1 over s plus 1, and x2 over x1 is 1 over s minus 1. Okay, so that means we usually go from a differential equation to the Laplace domain to create state space, but you can equally go in the reverse direction. What do I mean by that? I mean this is x1 times s plus 1 equals u, and the next equation is this x2 times s minus 1 equals x1. Right? This is you just multiply that. Now you know S means differentiation. So that means x1 dot in time domain plus x1 in time domain is equal to u in time domain, and x2 dot minus x2 is equal to x1 in time domain. So now we have two differential equations. So that should help us determine our state space model. How? We now know that x1 dot is equal to minus x1 plus u, and x2 dot is equal to x1 plus x1 plus x2. Can you see that? And from there you can find your A matrix. The form of state space is this. We know X is made of X1 and X2, obviously. So we are looking for X dot. So X dot is minus 1 times X1, 0 times X2, and X2 dot is 1 times X1, 1 times X2. So this is X dot, a matrix A times X, plus another matrix times u. So we have 1 for x1 dot and 0 for x2 dot. So we have A and B matrices. Now the way I have it is, if you look at the block diagram, x2 is equal to y. So y therefore is 0, 1 times x. So I'm going to bring that up. So let me look at the definition of the second portion of the problem. So we are asking about the steady state response of a system to a unit step input. What is the steady state response to a unit step input? So we can find, so we are looking for, so if u of t is 1t, which is a unit step input happening at time equal to 0, we are looking for y steady state. And the way to solve it is through final value theorem. So y steady state is equal to s times 1 over s times the transfer function, which is 1 over s plus 1 times 1 over S minus 1 when S goes to 0. So what does this predict? It predicts that. It predicts what?
Y steady state is -1.
It predicts that Y steady state is -1. That's what it predicts. You put 0, S equal to 0. But that's not the correct answer. That is not the correct answer. So this is not correct. Because final value theorem has one condition. For it to work, final value theorem has one condition. And that condition is the system has to be stable in order for the final value theorem to work. So what I wanted you to realize is that this system has two poles. This system has two poles. Where are these two poles located? Let's put them on the complex plane. One of them is located at -1, but the other one is located at +1. What is a system that has a pole at +1? What kind of system is it? It is an unstable system, which means what? Which means you give it a limited input, like a step input, but the output of the system just simply grows without bound. So it's an unstable system. And you can see that in MATLAB. So if you create a transfer function, so create a transfer function so G is 1 over S plus 1 times S minus 1, which will give you 1 over S squared minus 1, by the way. Then you can look at step response of G. And look at it. Does this go to -1? Of course not. This is an unstable system. So the point of this problem is don't apply theories blindly. Okay. The next step was to design a proportional controller for this system and find the location of eigenvalues of the closed loop system and draw the root locus. So let's do it here. So you can create the root locus, R locus of G. So with the proportional controller, basically what you are going to do, or what you're going to be able to do is, remember, we have a pole at +1 and a pole at -1. When open loop, you have these two poles. Now when you close the loop with a proportional controller means you simply feed back only the output and then multiply it by a gain and use it as an input. As you increase the controller gain, you're able to displace this otherwise unstable pole and bring it closer to 0, which is much better than having an unstable system. So with proper value of k, you can actually bring both poles to 0. Now this is not an ideal system. We would have preferred to have a pair of poles that are to the left of the imaginary axis. But being on the imaginary axis is much better than having one pole on the right side of the imaginary axis. So it is not completely stable, especially when you start going up, starts oscillating a lot, but at least it's not growing in response without bound. So that's the answer for the second point. And you can analytically also find that if you solve the problem. So how do you solve this problem? What you need to do is you need to realize that with proportional controller, so proportional controller, otherwise known as output feedback, A of closed loop is equal to A minus B times K times C. Is that right? Okay, so find B times C. So this is your B matrix. This is your C matrix. So B times C is 1, 0 times 0, 1. So 1, 0, 0, 1. So that gives you a 2 by 2 matrix. Row 1, column 1 is 0. Row 1, column 2 is 1. Row 2, column 1 is 0. Row 2, column 2 is also 0. And our A matrix is minus 1, 0, 1, 1. So A closed loop is, so look up again. Minus 1 is subtracted by 0. So minus 1. By the way, this needs to be multiplied by k. So when you multiply this by k, so you'll have a k here instead of 0. So minus 1, and then you have 0, 0 minus k. So it gives you minus k here. Then the next row is 1 and 1. So 1 minus 0 is 1. 1 minus 0 is 1. So this is your A closed loop. Now let's look at the eigenvalues of the closed loop matrix. So lambda I minus A closed loop will give you lambda plus 1, k minus 1, lambda minus 1. So that is lambda squared. Minus 1 plus 1 is 0. Minus 1 plus k equals 0. So the two lambdas are located at lambda 1 and 2 are of closed loop are located at the square root of minus 1 plus k. Did we do this correctly? Let's double check. So B is 1, 0. C is 0, 1. So 1 times 0, 0. 1 times 1 is 1. 0 times 0, 0, 0. So we did this correctly. And A was minus 1, 0, 1, 1. So A minus 1, 0, 1, 1. So we just need to subtract this. So we got this. And then A, lambda I minus A, so lambda plus 1 plus k minus, and lambda minus 1. So lambda squared plus lambda minus 1 minus minus. So that's correct. So the mistake that I have is in here. So when these go to the other side, the sign changes. I apologize. Let me correct the sign. So this is positive and this is negative, because they go to the other side before taking the square root. So lambda 1 and 2 is square root of 1 minus k. Okay, so where are the two lambdas when k is 0? So k versus lambda 1 and 2. So when k is 0, where are the two lambdas? And plus, by the way, we need a plus minus here because we are taking the square root. So where are the two lambdas when k is 0? K of 0? Lambdas are located where? Plus 1, minus 1. So we have one answer here. Does anybody else agree that the two lambdas are, when k is 0, the two lambdas are plus, minus 1? Anybody else at all? Yeah? Okay, so we set k is 0, the two lambdas are at plus, minus 1. And it's expected. When k is 0, the two eigenvalues are exactly located where the eigenvalues of the open loop are located. So k0 is open loop. So at what k we have two repeated poles at 0? Look at the root locus one more time. At a specific value of k, the two poles come together on top of each other at 0, exactly 0. Can you see that? The two come together and then shoot up. So what value of k will give you 2 lambdas at 0? K of 1. So if k is 1, you have 0 and 0. So if k is larger than 1, what do we know? Look at the under square root. K with a negative sign is going to be larger than 1, which means you have a negative number under the square root. So you have an imaginary number. And that imaginary number is at plus minus j times square root of 1 minus k. So it's a pair of completely imaginary number. And the system would oscillate. Do you have any interest in simulating this in MATLAB? Maybe? So let's give it a try. So we have already defined, did we define our state space model? Not yet. So our A is, so what was our A? Minus 1, 0, 1, 1. So A is minus 1, 0, 1, 1. This is A of open loop. Then we put a semicolon and define B. B was 1, row 1, 0, row 2. So B is 1, 0. C is, what is C? C is 0, 1, and D is 0. So this is our state space. These are the 4 matrices. Let's make system open loop as state space of A, B, C, and D. So we have our state space model. Let's double check. Let's look at eigenvalues of A, just to be sure. Is it difficult to read the text from the back? Or are you okay? Can you read it all the way back? Okay. So I just resized it a little bit so you have a better. So I'm looking at eigenvalues of A, and they're located at 1 and minus 1. That's what we found already. So the open loop system has 2 poles, one at negative 1, one at plus 1. So let's now go ahead and create the closed loop A. So A closed loop, so we need to tell it what K is. So K, we said if K is 0, the system is open loop. If K is more than 1, we are going to have a pair of purely imaginary poles. So let's put it 1.5. K is 1.5. A of closed loop is equal to A minus B times C times K. And it's a lowercase k. So this is the new A. And let's look at the eigenvalues of A closed loop. If we have done it correctly, we should get 2 purely imaginary numbers for the eigenvalues. Are they purely imaginary? There's 0 plus minus j times 0.7. So they're purely imaginary. So then what you can do is you can create a closed loop system. So the same way we created the open loop system, you can create a closed loop system with now A of closed loop. So you modify A. You keep B, C, and D the same, but you modify A. So now you have a new system. The next thing you can do is you can look at step response of system open loop versus step response of system closed loop. So in comparison to open loop, the closed loop system remains flat. The reason is that the open loop system, because it has an unstable pole, it grows too much. So it's very difficult for us to see what the open loop system does. I just wanted for you to compare them. So next thing we are going to do is we are going to look at the step response of closed loop only. So it's easier to appreciate. And here what it does. It simulates. I'm sorry. Of course it simulates. It oscillates because it's a pair of purely imaginary poles that the closed loop system has. Okay, let's go back. Let me know if you have any questions about MATLAB. So we looked at, we showed the root locus. Let me, for future reference, put it in on here as well. So you have this, and then you have at 1 here, and then it moves and goes up, and it moves and goes down. That's the direction. So this is k of 0. This is k of 0. Here exactly is k of 1, and this is k larger than 1. Here is also k larger than 1. So that's our root locus. So the real axis, and this is the imaginary axis. So that's what the output feedback can do for us. Let's go back to the problem one more time. Find location of closed loop. And we discussed about the expected change in response. So we discussed that as well. And we looked at the step response in MATLAB. And the next question is this system controllable? And the way to determine if the system is controllable or not is to create the reachability matrix. So let's go ahead and do that. So we need to create WR. This is a second order system. So we have B and A times B. So let's go ahead and calculate A times B. A was minus 1011. So A times B. And B is 1, 0. So row 1 times column 1 gives you negative 1. And row 2 times column 2 gives you 1. So W reachability therefore is 1, 0, minus 1, 1. And its determinant is 1, which is definitely non-zero. So the answer is yes, controllable. Which means through state feedback, you can place the poles of this system anywhere on the complex plane that you want. It's possible to do it. That's the meaning of controllability. So what it means is we can place, so the meaning is place closed loop eigenvalues anywhere on the complex plane. So it's possible. That's the meaning of it. And the next question asks to design an output feedback controller for a standard second order system. Explain how the controller gain affects the response of the system, and then repeat the same thing with this time for a state feedback controller. So we are going to contrast two different controllers for this second order system, a standard second order system. Did we solve this problem already? Can you check to see if we solved this problem? I know we looked at this problem. So in a way, we solved this problem already because this is the system. Even though we don't present it as a transfer function, we have solved the problem for the state feedback. What we could repeat is to solve the problem for output feedback. Or have we already solved this previously? Output feedback. When you worked on the quiz, did you come across a complete solution of this system with output feedback only? You didn't take the quiz, any of you? Or you don't remember? Did you see the solution of this with output feedback only? So we can do the solution for output feedback. So what we are going to do is we are going to solve this problem that we solved with state feedback, now with output feedback. With state feedback, we saw that we can place the eigenvalues anywhere on the complex plane. So why don't we go ahead and create an output feedback for the same system with the same numerical values, so we can talk about comparison. So this is our A matrix, B matrix, and C matrix is 0, 1. So let me go ahead and add a slide here so it's separate from the rest of the solution. Did we not add? Let's do it again. So it's after 307. Okay, so we are now going to design an output feedback. Okay, so output feedback, which means U is negative K times Y, which means A of closed loop is A minus B times C times K. So there's one controller gain, as opposed to the previous case where we had two controller gains. So let's go ahead and calculate B times C. So B was, what was B? 0, 1? Yeah, B is 0, 1. So let's go ahead and calculate B times C first. So B times C is 0, 1. And if the output of the system is the displacement, C is going to be 1, 0. So that gives you 0, 0, 1, 0. So B times C times K then becomes 0, 0, K, 0. So A minus BC times K is going to be equal to, so for A we had 0, 1 minus 1 minus 1.4. So 0, 1 minus 1 minus 1.4 minus 0, 0, K, 0. So again, a 2 by 2 matrix, subtracting, you get 0 here, 1 here, minus 1 minus K here, minus 1.4 here. So this is A of closed loop with an output controller, or otherwise known as proportional controller. So what we can then do is to look at lambda I minus A closed loop. So this is A closed loop for this case. So lambda I minus A closed loop will give you lambda here, minus 1 here, 1 plus K here, and lambda plus 1.4 here. So that's so we are going to look at the determinant of this matrix. So this is the matrix, and we are going to look at its determinant. So the determinant is going to be lambda squared plus 1.4 lambda plus 1 plus K equal 0. Yes.
So for that 1.4, which
Where did we get it?
yeah.
Good question. Let's go back. So you remember when we set up this problem, we found A matrix to be 0, 1 minus K over M minus B over M. So that's the general form. That comes from the differential equation. And then later on, when we solved the previous section of the problem, we assumed numbers. So we said M is going to be 1, K is going to be 1, and B is going to be 1.4. And
So on the quiz for the problem, we're expected to just assume some numbers and solve it.
no, you could have kept B, K, and M.
Yeah.
The reason I'm assuming these numbers is to be able to compare it to the previous case. So if you keep B, K, and M, you get the exact same type of response. So you get the trend as we will find it shortly. So you didn't have to assume any numbers. Okay. So this is lambda squared plus 1.4 lambda plus 1 plus K equals 0. Now, as usual, if you take this and compare it to the standard second order characteristic equation, which is lambda squared plus 2 zeta omega n lambda plus omega n squared, what do you see? What do you recognize by comparing the two? While you're thinking, let's deploy MATLAB here. So A for us is 0, 1, minus 1, minus 1.4. That's A. B is 0, 1. C is 1, 0. And D is 0. So what do you see? You see as you increase K, what is happening when you compare these two equations? So let me write it down here. As K goes up, which is the proportional controller again, right? Right? Okay. So as K goes up, what is happening? Natural frequency goes up. Right? But the way natural frequency goes up is not completely under your control. It increases as much as you want it to increase, but on this root locus. So open loop has two poles with these numbers that we assumed. Open loop has two poles located at negative 0.7 plus minus 0.7. Can you see that? Open loop has negative 0.7 plus minus 0.7. We intentionally created these two open loop holes. Now, as you increase K, what is happening? The two poles are moving farther away, keeping the same real part, but the imaginary part gets larger and larger, which means omega n is increasing. The distance to the origin is increasing. But what is happening to damping ratio? It doesn't. It appears that from the equation that it stays the same. But move on this blue curve as you go up. Damping ratio definitely goes down. As you go up, the angle with the imaginary axis goes down. On the surface, it may appear that your damping ratio doesn't change, but the way you can see it changes is this. So let me write it down and I'll justify what I mean. So omega n goes up, but damping ratio goes down. Why? Look at this. 2 zeta omega n remains equal to 1.4. I give you that. 2 zeta omega n remains equal to 1.4. It doesn't change. 1.4 doesn't change. But as omega goes up, what should happen to zeta to maintain 1.4? It has to go down. Do you see that, everybody? So that's what is happening. So again, we go back to the limitations of output control versus state control. In state feedback, we were able to put these poles anywhere on the complex plane that we wanted. We were able to do that. But here, we are bound to this root locus. We are bound to the root locus. We can speed up the system. We can increase omega n and get a faster reaction from our system, but we are losing on damping ratio as we increase K. So if you look at step response of system, which is open loop, this is the way open loop behaves. So you have a bit of oscillation, but not much. It's 0.7. But if you now create your closed loop, so A closed loop, which is A, so we need to decide what K is going to be. Let's say K for now is 1. Let's go back and see. If K is 1, it gives you a larger natural frequency. So square root of natural frequency is 2. So natural frequency would be square root of 2, basically. I'm sorry, squared of natural frequency is going to be 2, so natural frequency is going to be square root of 2. So let's go ahead and with K, create a closed loop, which is A minus B times C times K. And then create our closed loop system as state space with this new A, B, C, and D. And then we are going to look at step response of open loop next to step response of closed loop. I'm going to give pause here so nobody is typing along. Okay, so let's look at the step response. So again, because the steady state response is different, it's difficult to see them in. So let me remove the open loop and then keep the closed. What did I do wrong? Yes.
You have A, it's supposed to be A minus B, CK, you have A equals.
Yeah, thank you. Thank you. So let's put that back. So let's. Why the same thing? So A is 1. A minus B times C times K. Let me see what did I do. So so this is A closed loop. Let me look at eigenvalue of A closed loop to see what I did wrong. So eigenvalues of A closed loop are not supposed to be at 0 and 0. It doesn't make sense. So what is C? C is 1 and 0. What is B? 0 and 1. What is A? Oh, our A is incorrect. So I did not put A in. So our A is supposed to be 0, 1, minus 1, 1.4. I thought I did it. So 0, 1, minus 1, minus 1.4. So that's our A. Let's try it one more time. Okay, here. So you can see now that the closed loop starts oscillating a little bit more. So as you increase K now to a larger number, so let's say K is 10, the amount of oscillation, even though, so the difference is the steady state response goes down. So if you take that out of the equation for now, you can see that the closed loop system oscillates more because we are losing on the damping ratio. So the closed loop system is now overshooting like 40%, as opposed to open loop system that didn't overshoot as much. So it basically reduces the level of damping ratio. So go back to so this is the quiz solution. So we covered all the questions of the quiz. So let's look at now another problem. And I'm going to give you some time to set this up so you can follow along. So the next example is this. So we have a mass and a spring only. So there is no damping. So a mass spring system, no damping. And what we want is to look at the effect of base motion. It's like a suspension system. So what do we mean by base motion? Is that this is M. It is attached to a K for stiffness. And this is moving, so it's not stationary. So the displacement of the base is xb, and the displacement of the mass is x. And its velocity is v. So the first step is to come up with the differential equation for the system and set the state space model. And the question is, how is output feedback for this system different than state feedback? This is a second order system, so it has two state variables, both position and velocity. So we want to look at and contrast these two controllers for this system. So I'll give you a couple of minutes to set it up, and then I'll go over the solution with you. So the assumption is that x, the displacement of the mass, is measured from the static equilibrium. So weight has been canceled with the initial deflection of the spring. So when you draw the free body diagram, weight doesn't come into play. So the free body diagram M and there is one force of spring here, and this is displacement x. So the differential equation therefore becomes mx double dot is equal to force of spring, which is equal to k times x of base minus x. So you can rewrite this equation as mx double dot plus kx is equal to k times xb. So if you take this differential equation and divide it by m, you get x double dot plus k over m x is equal to k over m x b. So we are going to call this our input, k over m times x of base. Okay, so speaking of setting up the state space model, x vector is going to be made of x and x dot, which is position and velocity of the mass. Our input is given here, and our output is displacement of the mass. So we are now ready to go ahead and create our state space model. So x dot is equal to 0, 1, minus k over m, 0, plus 0, 1. Oh, I'm sorry, I forgot to put x in here. So times x plus 0, 1 times u. So the second line, this line of the state space model, basically replicate this, except that we don't have k over m here because we called k over m times xb. This entire portion, we called it u, so then 1 is multiplied by u. So x double dot, which is the derivative of x2, is equal to minus k over m times x, which is the first state variable, plus 0 times x dot. So that's why the second element of row 2 is 0. So we have what this, and then the second portion of the state space model is this 1, 0 times x, and d is 0. Let me give you some time to catch up to this stage and let me know if something is unclear for you. So we have the a, b, and c, and d is 0. We simply didn't write it. Okay, so what are we trying to do? So we are trying to contrast the two control methods that we have covered so far. Output feedback versus state feedback, and see what they offer in terms of degrees of freedom. What do they offer in terms of us being able to put the eigenvalues where we want them to be? So let's start by finding the open loop eigenvalues. Where are they located? In order to find them, we are going to find lambda I minus a. Where do you think the eigenvalues are located without us finding them? How will this system behave if you give it a movement to the base, a constant movement? Just push it up by a constant level, which is a step input. What will happen to this mass? Will it oscillate? Will it oscillate? It will. You have a spring, it stores energy and it releases energy. Will that oscillation ever decay? What causes the decay? Is there a damping? So will that oscillation decay? No. So based on this behavior, what is your prediction? Where are the two poles located? So you have oscillation with no damping. Where are these two poles located? It essentially means damping ratio is 0. So damping ratio of 0 means angle to the imaginary axis is 0. So you are on what axis? You're on the imaginary axis. So our prediction is we get two poles that are purely imaginary. Let's see if we get that, or did we do something wrong? So lambda I minus a is equal to lambda minus 1 k over m lambda. Find the determinant. Lambda squared plus k over m is 0. So lambda 1 and 2 is equal to plus minus square root of minus k over m, otherwise known as plus minus j square root of k over m. So you have two poles, locate, and they're imaginary, plus minus of j times a number. So that's the open loop. So open loop eigenvalues. So where are they located? If you create the complex plane, they're located here and here, where this is square root of k over m. And this is minus square root of k over m. So the open loop system is problematic, which means what? Which means you just give it a simple step input and it keeps oscillating forever. That's not a desirable response. You want this to gently move, follow the input, but we don't want oscillation to stay around forever. We want to be able to have a smooth transition to a steady state response that is not changing all the time. That's not a desirable system. So we are going to start with designing an output feedback. So output feedback. So the first thing is we're going to do so I screwed this up. I apologize, this is not cooperating. So for some reason this stopped working. So why don't I stop here and let you continue this example. So design an output feedback, a state feedback, and then we'll work on it together. Thank you. Yes, sir.
Quick question.
Mhm.
For the second one, the answer for this is that you can't find a steady state response because of the positive pole, meaning that it's unstable.
So it doesn't have a defined state.
Gotcha. Okay.
Yeah.
Thanks.
Is this the second? When was the last quiz? So if it's the second, I don't think it's, is it? I can look it up. I don't remember when was it due. So if it is the second class, there would be a quiz, but I don't remember. I'll check it out once I get this to work. I might. Hmm.